Buongiorno. It was really a great honor, to have accepted this invitation to speak to this very, very prestigious university, which we are trying to inaugurate the 659th, anno academico. This is incredible. And I'm very proud to have been asked to do that from my friend Orazio Svelto, Professor Svelto, and also, of course, a new rector, and Francesco Svelto. I really listened to the debate that Italy now is facing about supporting the the research and educations, universities. For me, I have a very, very simple way to look at research in society. Okay, it's like a locomotive pulling a train, and if you don't really feed the locomotive, the train is not going to move. So I think it's very, very important to think about this type of thing because, of course, we cannot imagine Italy, which has been so prosperous, which has been so, the light, and where everything started, to fall behind. So I hope that maybe under the leadership of Francesco Svelto, not only here but also in other universities, you will be able to keep your students. In France, we are seeing many excellent students from Italy. And I think this is maybe not really the right thing. I think Italy should do its best really to keep their students, Of course, the student has to go and learn elsewhere, but they have also to come back. Okay, so I'm going to stop here. That was my short introduction. And I'm going to tell you now about my passion for extreme light. And, okay. And I have to say that, that the Nobel Prize is always announced the first Tuesday of October, and at around 11, 12 o'clock. And this day, in 2018, I was going to the swimming pool, like I'm doing every day. And my secretary ran after me and said, Gérard, come back, because we have this phone call, from a foreign country. So I came back, pick up the phone, and on the other, on the line, the person introduced himself as being, is it me? Is it me? Yes, it's me. I did it again. Yeah. I told my wife, Marcel, said, remind me, to turn off my phone, Anyway, so I was really on the other side of the line, on the other end of the line, I had the chairman of the Nobel Committee saying, Professor Mourou, I'm really very pleased to tell you that you have been selected as a 2018, Nobel Prize, and you are going to share this prize with Art Ashkin, but more importantly, with your former student, Donna Strickland. And of course, it was incredible because I knew that very, very few women had been the Nobel Prize, had won the Nobel Prize, but I didn't know how few it was, okay? And it was, in fact, Donna Strickland was the third Nobel Prize in 120 years. We had men had, won something like 200 Nobel Prize, but women only 3. So I think, of course, I was very, very pleased to have myself, to get myself the prize, but I was also, of course, extremely pleased to have been the advisor, the mentor of the third Nobel Prize, since creations. So it was a fantastic day for me this day. Okay, so let me tell you now why we got the Nobel Prize. Okay, let me see. So it is about light, about research. And what are we doing when we do research? Well, in fact, we are trying to find where we are coming from, who we are, where we are going. It boils down to this. And so that's why I picked up, this very nice, of course, masterpiece from Gauguin to illustrate my friend. Now, everything started from, of course, the Big Bang. 14 million years ago, billion years ago, we were all together in these teeny tiny volumes, which was much less than the volume of an atom. And that was really the Big Bang. And the light came about 400,000 years after the Big Bang. And what I'm going to show you that during the work that I'm going to show is the fact that we are trying now with lasers really to come closer to the Big Bang. So let me tell you about light. So you have basically until 1960, all light was incoherent. And incoherent means that, and in 1960, light we were able to produce light, coherent light. And that was the laser. So you can see the difference already. In this case, in the first case, of course, the light, is produced by this, lamp, and all the photons are going in every directions. The photons also, light is white, so it's composed of all the colors. So it's kind of really incoherent. And in this case, of course, the light, you will see, much well behaved. And the light is going into one direction, and the color is about the same of all the photons. And the incoherent light, just to explain to you what it is very much like marathons, runners, Marathon runners, they are all different, of course. They are dressed differently. They have different size. They run at different pace. And coherent light, laser light, is very much like this, okay? Like a soldier, marching down an avenue or something, All the soldiers are the same. I mean, dressed the same, I would say. And they move at exactly the same pace. And, from one soldier, you can figure out the position of every one of them. So, this is this very well organized system, is very much like, troops, is very much like lasers. Now, lasers, can be continuous or pulsed. The pulses can vary immensely. It can vary from, milliseconds, microseconds, nanoseconds, picoseconds, femtoseconds, attoseconds, and maybe soon to be zeptosecond. So every time you have 3 decades, okay? So, and, you can, of course, you can, this is one of the reasons why there's so many applications, of laser now. So in all my talk here, I'm going mainly to talk about femtosecond pulses, okay? Now, one of the, by the way, before I move on, I want to try to introduce the first person who really produced coherent light, okay, and made the laser work. And the person is Ted Mayman. That happened May 16 in the afternoon, 1960. For the first time, man, produced coherent light. When you think that for 40 billion years, the light, was emitted incoherently, now, 50 years ago or so, the light has been emitted coherently. Now, I'm going to talk about extreme light. So what makes this light, I'm going to talk to you, extreme, is the fact that they are extreme because they are extremely short. The durations is femtosecond, 10 minus 15, okay? During this time, the light itself propagates about a micrometer, okay? And what is incredible is the fact that now, with this extremely short burst of light, if we're producing a little bit, a little amount of energy during this time, like 1 joule, of energy in 1 femtosecond, well, this is in fact, that will correspond to a power of petawatt. Let me tell you what a petawatt is. So you see, because power is energy divided by time. So even if you have a small amount of if you provide a small amount of energy, but because the time is extremely short, you are going to get extremely high peak power. And in the range of petawatt. Now, petawatt, what is it? Okay? You see, this is a power stations, producing electricity, and typically these power stations are about a gigawatt. They are really big, okay? We have about 60 of them in France. I'm not sure about in Italy, maybe something like this. But for the petawatt, you need to have a millions of that. So it's a millions times the power produced by these power plants. Of course, during only a femtosecond. Now, it's another way, I mean, say, you know, look at the power of the world grid power, okay? The world grid power, electric power, is typically of the order of terawatts. So these petawatts, you know, are of the order of 1,000 times the world grid power. Okay? So it's very respectable. Now what is exciting is the fact that we can take this power, enormous power, and we can focus it on a very teeny, tiny spot of the order of 1 micrometers. So the intensity that we can produce is absolutely enormous. And we can also, because the intensity is also of light, you know, is producing light pressure, okay, radiation pressure, and this radiation pressure is enormous, you know, at this level. It's about 100 or tens millions of these Eiffel Tower on the tip of your fingers. So you would not really expect that from light, you see? But this is, we can do with very extreme light. So this extreme light, you can really produce the largest peak power, as I say that, the largest temperature, the largest pressure, the largest accelerations. And it is really the universal source of high energy particle and radiations. And I'm going now to really show you what I want to say. Can I have a, oh, okay, I have a laser here. I didn't know. I'm not in my lab, so I'm lost. So you know, let me show you when the laser was invented, okay, by 10 Maiman, demonstrated, the intensity is in watt per square centimeter, but whatever. You know, it's relatively low, okay? Of course, it was much, much higher than any kind of existing source, but nevertheless, it was relatively low compared to what we can produce now, okay? And then quickly, that was 1960, quickly, the light, the power grew up, and then to a certain point, about here, 10 to the 14 watt per square centimeter or so, and then the power stopped. The power stopped, but we couldn't really go higher because simply the power was so large for material to sustain it, so you were basically damaging the material, so you couldn't go higher. So you had this plateau for about 20 years. And in 1985, we invented this concept of chirp pulse amplification, who made possible, really now, to go much, 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 much higher in intensity. Because I know you may not be familiar with using exponents, you know, to characterize power. So I use maybe this, trying to image, you know. If we say that in this regime, intensity was of the order of a fly, the weight of a flight. Now we will be able really to produce something as big as maybe 100 elephants, you know. So it's huge. It's a huge change in power, and this, of course, this is going to correspond to very large change in the applications. And it's what I'm going to describe. Okay, so I'm going to start from the, let's see, I'm sorry. I want to try to say something important, is you know, I got the idea. It was very simple. I got the idea. I'm from Savoy. I like to ski. And we were in the States with Marcel and me, you know, going to a chairlift. And then I thought about this idea, how we could circumvent this problem of damaging the material. And you know, when you ski and you take the lift, you know, I mean, it's very nice. It's, you know, you have sometimes the sky is blue, and there's beautiful snow, so, you know, it's nice, okay? So it invites, you know, dreams. And it's where I really thought about this CPA. And I told my wife, oh, Jesus, I have this incredible idea. And I have to go back to the lab. And it's what I did. I went up and to the top of the chairlift, and then I went down as fast as I could to pick up my car, and Marcel was, you know, stayed with friends. We were with friends at that time. And okay, so I came back to the lab and I say, well, guys, this is what we are going to do. And what we are going to do is the following. We start with very short pulse. And I have the pleasure, I have to say, that we have really one big expert in the audience here, Professor Svelto, okay? Anyway, so we have very short pulses, and if we take these pulses and we try to amplify it, this is where we have a problem. We have a problem, we are going to damage this amplifier. But before we do that, I said, well, before we amplify directly, what we will do, we are going to stretch the pulse. And we are going to stretch pulse with what we know are dispersive elements. So now, you know, this pulse is going to be stretched. Or red in front of blue, or blue in front of red. And then, of course, we are going to decrease the intensity of the pulse, okay? And then we are going to be able now to amplify the pulse by a large amount. If we stretch it by 1,000,000 times, we are going to amplify it 1,000,000 times better, okay? And then once we have stretched the pulse, okay, we have extracted all the energy from this amplifier, then we are going now to compress it back to the initial value which we started with. But now the pulse is absolutely gigantic, okay? So this is the concept, you know, and it was a really good one when I thought about this, you know, because I had 30 years later I had a Nobel Prize, you know. That was great. Okay, so now I'm going to show you some applications. Applications, you start with, so I will describe only a few, of course, because I don't have the time. But we are going to start to describe the application in the purple area, and I will try to explain the one in the green and then in the yellow area. Okay, so let's start with the purple area. Micromachining. I mean, we know that lasers are already involved with micromachinings. But the pulses were longer. They were not femtoseconds, they were microsecond, nanosecond, and things like this. So if you take a pulse which is relatively long and you shine your target where you really want to micromachine here, of course, you know, because the pulse is long, so the heat is going to sink in longer times, and what you are going to do is to make really a large crater. So you are not going to have very clean details. Of course, it's better when you are using nanosecond, and even better when you are using femtosecond. Femtosecond, the light, is absorbed so fast, and the temperature goes so fast, but it doesn't have the time to move. And so you get very, very clean result. So this is an example where the pulse was about 10 to the nanoseconds. So you see that if the pulse is long, you have craters. You have it's a kind of garbage. And but now, if you are using femtosecond pulses, then it's what we get: pristine holes without any damage. Collateral damage. Okay, so this is very nice. And what is nice also is the fact that, of course, light can be transmitted through transparent material. And if you are focusing the pulse into this, in the bulk of this transparent material, then you can really produce bubbles, really small bubbles. And if you move your laser here, you can produce a series of bubbles this way. Now, this is, of course, very nice because the applications was in ophthalmology, was precisely where you want to have precisions. You don't want to have collateral damage and so on. So here you see that you have a cornea, for instance, okay? And if you focus the pulse into the cornea, you can make what we say flap. And with this, and so you can correct the visions of the patient. And now, this technology is used and has been used on 24 million eyes. Okay, so I'm sure in the audience, many of people got this procedure. I don't know how much time do we have? Do you know? Okay. Because I wanted to tell you the story about this, showing that discovery happens sometimes. 15 left over. Okay. 20 minutes left over. Okay, good. So I have time to tell you the story. Okay. So we were the first trying to get to be able to produce these femtosecond pulses. One of my students, was aligning the laser, and bang, at that time, the goggles were not really very, very good, and so on. So they were lifting the goggle, and he got a laser in his eye. Okay, so he came in my office. He was completely destroyed. Not because he had a laser in the eyes, because because he thought that we were going to close the lab, with his thing. So so he was really completely, So I told Dita, don't worry, let's go first to the hospital, and we will worry about the lab later. Okay, so we went to the hospital. And then the young medical doctor, he was an intern, looked at the eye of my student, looked at his retina, and he couldn't believe it. He could not believe it. And he asked Dita, my student, said, what kind of laser do you have? And he said, well, we have a femtosecond lasers. Most of the time, the ophthalmologists were working with nanosecond and much microsecond lasers, but it's a femtosecond laser. But why are you asking that? Well, I'm asking you because the damage is perfect. Very perfect, no collateral damage, very clean. So immediately, this young doctor, Ron Kurtz, his name is, he was at Stockholm when we got the prize. He said, well, can I call your advisor, I said, yeah, of course, you can. So he calls me and he said, well, I was examining your student and I would like to work in your lab, use your lasers. And then they work very, very hard. And 8 years later, you know, he got with this product. They sold these systems, you know, left and right. So anyway, so this sometimes, you know, serendipity help, you know. Very good. So this is really an example of flap cutting, you know, with 50 picoseconds or femtoseconds. You see the difference, enormous difference. And so now, told you a little bit about ophthalmology. Let's go now to the next level. Okay, so we are increasing the intensity now. Okay, and we are in a green area. In a green area, this was an area which was completely novel for optics, because the motion of the electrons, you know, which are, I would say, dancing around the nucleus. Normally, with ordinary light, the velocity is not great. It's not large. It's not, you know, it's not as large as. It's a very small fraction of the speed of light, say, okay. But when you are at this regime 10 to the 18, what happens is now the electrons, which are moved by the laser field from the laser, now becomes relativistic. But it is the mass of the electron changes, and also the fact that you have this V cross B, which, because the velocity is becoming as large as the speed of light. So this is a completely new era, okay, and led to really new novel application. And one of the applications is really important. It is in, I would say, in particle accelerations. Particle accelerations, you know, you may say, okay, accelerator, well, what's this, okay? Well, I mean, what's this? Is the fact that this is really used extensively, of course, for material science, but also in a medical. In a medical, we are using a lot of accelerators. But the accelerators are big and expensive. And you will see that now with the laser, we can accelerate the particles with systems which are 1,000 times less bulky. Okay? So, and the concept of this accelerator has been really proposed by my good friend Toshita Jima in 1979. So that was before the CPA. So he proposed the concept, and when the CPA came along, you know, 7 years later, well, we could really start to do the experiment. But anyway, so what is now, we are going to accelerate particles with light, okay? And I will show you how it is. It's very analogous to this surfer surfing, in fact, on the wave, but we are going to replace the surfer by particles. Okay, so here, this is a generations of really very, very large electric field produced by laser. First, we start with the laser, you know, the extreme light laser. We focus this into what we call a gas jet, okay? And we are ionizing the atoms of the gas jet. And what happened, you are going to produce what we call plasma wave, okay? Plasma is a soup of electrons and ions. And so you are going to have, you know, very much like I said, you know, at sea, you have these waves, and now the electrons will go in this wave and will be accelerated by the laser. And but what is amazing is now the accelerations. The acceleration is in a GeV per centimeter, giga electron volt per centimeters. Conventional, if you want to produce giga electron volt, you need a machine like this, okay? This is typically synchrotrons, 3 GeV, but it's not 3 centimeters, much bigger, of course. And of course, the cost, of course, is much bigger. So that, of course, is very, very important, and we are going to meet with Carlo Rubbia in a couple of days, in 10 days or so, trying to really change the paradigm of accelerations. Okay, so here, just to give you, so here maybe you recognize this is the TeV accelerator at CERN, okay, so LHC accelerators, okay? And it's 27 kilometers inland because we can only accelerate particles, of 1 MeV per centimeters. Now, if we do 1 GeV, it's 1,000 times bigger, so it should be 1,000 times smaller. So, and that's the idea. If you really go from microwave cavity, which is really what's being used for acceleration of particles, it's 27 kilometers, but if you go now to laser wake field accelerations, now you start to have size of the football field. Much bigger, much really, of course, shorter. And now we are even working on system which has even more which are even more powerful. We are working with solid and instead of gas, and then we are expecting gradients of TeV per centimeters, which means, like CERN, 27 kilometers now, once again, on tip of your fingers, okay? And so this is remarkable. In fact, I want really to mention this, and I want to mention that in front of students here, because I want to tell them that, the best is really yet to come, okay? That's a very good example. So let's go on. Now, when we go into this yellow area here, when we are increasing these laser systems and we are building new laser, the ELI facility, for instance, and then what happens is you can really we'll be able really to produce fields which are enormous, so large that you are going to break down the vacuum. You are going to boil the vacuum, okay? And so this is what we are really aiming at. Why do we do that? Well, it's exactly, to be one step closer to the Big Bang. There's a lot of things that we don't know about. Here we will be able really to produce, at least to produce things on the tabletop, astrophysics on the tabletop, or astrophysics in laboratory, trying to explain what happened, 14 million years ago. And trying to understand also how light, for instance, light really propagates in vacuum, which is not really something obvious, and for trying to understand where is black matter and so on, dark matter and so on. Okay, so now the other things that we can do, okay, besides boiling vacuum, okay, is something very, very important in the medical world. For instance, here, we are talking about, because we are capable of producing very efficiently high energy particles, trying to shrink the size of these accelerators by a large amount, so and also shrink the cost, which means that we should be able really to produce this type of accelerations, throughout the world easily. So I'm going just to describe something that could be done, is what is very attractive, is what we call proton therapy. Because now we can accelerate protons, we can accelerate electrons and so on. And let's suppose that if you have a tumor which is really within, tissues which are healthy tissues, okay? If you are using really electron therapy or X-ray therapy and so on, you want really to burn the tumor. So you will have to go focus on your tumors. But as you do that, you are going to burn also the healthy tissue which are before the tumor. And so it's not very exciting, okay? On the other hand, if you are using protons, then all the protons are going to stop at what we call the bright peak. And we can adjust the bright peak as a function of the energy of the pulse. So we have a way really to deposit the energy, within the tumor and not outside the tumor, not on the tissue before the tumor. So this is, of course, a very, very important thing. If you can make really small systems, which can go into hospital, which are affordable because they are less expensive, this, of course, is very, very expensive. I'm not going to discuss the other one because of lack of time. But anyway, this is just to give you an idea. Now, the other very, very important applications is in terms of energy. We know that we have a problem with the energy. We don't know how to produce energy without destroying the planet, okay? And we can see the effect now, okay, the climate change and so on. So the idea we thought, and which is very attractive and elegant, is trying to do to transmute what we call the minor actinide. Minor actinide are really the nucleus which are of large elements, and you have four: neptunium, americium, curium, plutonium. Okay, these are really the bad guys. Okay. And so if you can come and produce neutrons, and we can produce neutrons with our extreme light laser, then you can shoot at these neutrons produced by a relatively compact system and so on to the element and to the waste. And then you can fission this element in fission product. And now these elements, they don't have millions, for like 2 million years for neptunium. Now you can go to minutes, okay? So, of course, this is that will be absolutely fantastic. If we could do that, if we could demonstrate that, this is what we are trying to do now, okay? And, we have people like this, okay? Very interested. And I am with Donna Strickland and myself, and we are talking to the Pope about this technology. And he's a fantastic man, okay? And he told us, if we, of course, can demonstrate that, humanities are going to owe you a lot. So that was nice. And so this is the type of things I'm really excited to show that here. Now, another big important thing is really that we have to solve is since 1957, you know, the year where the Sputnik was launched, then we have launched, of course, many satellites, and we have really created a huge amount of debris. These debris are going at 10 times the speed of the fastest bullet, okay? So it doesn't matter how big they are going to be harmful. And so this is the amount of debris. You see, always takes Eiffel Tower as a, so this is the amount of stuff that was sent in space, okay, until now, okay? 28,000 tons is 4 times the Eiffel Tower. And there's about 1/2 of Eiffel Tower, which is under the form of debris. So we will actually now to, of course, trying to clean the space, okay? And how we do that? Well, we have, okay, let's see, no, I'm going, yeah. So the idea is that we are going to use a laser that we are developing for the other extreme light applications. And this laser will be really put first on the space station, so over element. And so when we see debris coming, okay, about 100 kilometers for debris of about a centimeter size, then we can shoot the laser. We are not going to explode the debris because we could really create even more debris, okay? But we are just going to ablate just a teeny tiny part of the debris, and that is going really to produce a rocket effect. And this rocket effect is going to deorbit the debris in the atmosphere and will be burned in the atmosphere. Now I'm going to show you a short clip demonstrating this. And this is the story that I'm going to show you is start with a real story. It is a story which happened in 2007 when the Chinese tried to destroy one of our satellites with one of our missiles. They tried to demonstrate that indeed they had the capability now to destroy satellites, you know, to other countries, of course. So, but doing that, they blew the satellite and produced tons of debris, millions of debris. And so that is, this is what I'm going to show you. And I will show you our laser systems that we would like really to use to clean up the space, and which is based, in fact, on fiber lasers. And yeah, and so it's a short movie, but I think it will make the point. So here with, so this is really the missile going and trying and destroy the missiles, I mean the satellites, okay? You see that produce millions of debris. Now this debris moves at 10 times the speed of light, the speed of fastest bullet. And now this is a laser, you see, used with fiber lasers that we can, we call ICANN, we can use now to ablate a fraction of the debris. So when we see a debris, we shoot the laser, we ablate a small amount of debris, and that is enough really to really change the orbit of your of the debris. Okay. So so now in conclusion, you know, the extreme light is capable de produire les champs les plus importants, les accélérations les plus importantes, les températures les plus importantes, les pressions les plus importantes. Donc elle offre vraiment de grands espoirs pour le futur de la science et la société. Et ça, c'est exactement dans l'esprit de... I'm sorry, I switch. This is exactly... Italian now. I'm going to Chinese later. Okay. And so this is really in the spirit of the motto of Alfred Nobel, who says that for the greatest benefit of humankind. Okay, now I ask, let's see that. I know people are always bombard us with me or questions, you know, about Nobel. So I'm going to show you a little bit, few slides about the Nobel ceremony. And so what happened after the phone call? You get, you know, the first Tuesday of October, okay? So what happened is, first of all, you have to give a lecture. Okay, you have to give a lectures. And so here myself giving lectures. This is Donna, okay? And we're together here. And then you have to learn how to receive the prize. So you have to practice. And this is what we are doing here with this lady, which is now trying to act as a king, okay? And so you have to learn how to bow, you know, to the jury, to the audience, to the king, and so on, you know, and you have to do that, you know, very well. This is us when we are looking at the other laureate, practicing the same thing. And after that, well, you have to get ready for the ceremony. So this is Marcel, here my wife, and Donna, taking care of my butterfly. Yeah. And this is now the audience, the theater, okay, where we are going to receive the Nobel Prize. So here you have the royal family, here. Here you have the member of jury, you know, and here you have the laureate, okay? So, and remember, I mean, this is physics first, so physics, chemistry, medicine, literature, and economy. So here are the kings, and so on, you know. And then you get the prize, okay? Get the prize, and you are very proud, okay? Very proud. And you are, okay, these are all the Nobel Prizes, okay? So this is of last year. And then you are congratulated by your wife, you know. You see, she has a beautiful dress from Dior, you know. She's beautiful. And then we have this huge, phenomenal banquet, okay, with 1,500 people, okay. So you have this big table here, that is a royal table, okay, and the laureate, you know, are at the center of this table, okay. For instance, so here we have Donna next to the king, because physics is first. Plus, I mean, she's a woman, so she has to be next to the king. Myself, I'm next to the queen. and Princess Sofia. And then, so this is really very glamour, okay? But nice. I mean, the entertainment is fantastic and so on. But the most moving things, emotional things, is this one. This is the most emotional moment of everything for us, for me, okay? I am with Marcel here, and so they take us, in this office, which is not glamorous, and they come with booklet, and these booklets are old. They are 120 years old, okay? And they have the signature of all the Nobel laureates. And this, what is really very moving, is the fact that they are asking you now to put your name on it. You have all this fantastic person, and so with Marcel, which we have been together for 52 years, and she supported the physicist, which is something incredible, and myself. I mean, we are very moved by this moment. Okay, I thank you very much.
So we really thank Professor Mourou for his outstanding, distinguished lecture, and for all our students that could listen from you. Mm-hmm. One thing, well, we learned a lot. Many things are yet to come.
Yes.
Applications in medicine.
Absolutely.
And another one for the younger. October 1st, please go swimming and keep your telephone on. This is our medal, dedicated to Maria Teresa. I told you that in the 18th century made a lot for the renewal of this university, and this is the highest honor we give to our host. So please.
Thank you very much.
Oops.
So,
thank you very much.
Very good.
Hope having you here again for some lecture, for something to do, because now you are in the full professor group, and maybe you can take the advantage, we take the advantage and have you here again. Thank you again.
Thank you. Thank you, everybody.